Hi everyone, Amy here as expected. And today we are looking at 4.2, which is covalent bonding. So we are going to talk about what covalent bonds are and how they're formed. We're going to talk about single, double and triple bonds, bond length and bond strength, and bond polarity. What I would like you all to make sure you've got is either a periodic table or preferably a data book that has that periodic table with the electronegativity values. So let's get started. I am going to be moving fairly quickly through here because a lot of this should be recap from Year 10 science for a lot of you. So covalent. So co means together. Let me just double check I'm recording. Yes, I am. And then valent refers to the valence electrons. So a covalent bond is a bond in which those valence electrons are shared. So in ionic bonding, our atoms got happy by either gaining or losing electrons in order to get a full outer shell. In covalent bonding, those atoms share those valence electrons. So let's pick the simplest, the very first covalent bond that's formed, which is between this hydrogen atom, and I'm going to switch, actually I'm not going to switch colours, and this hydrogen atom. Now, my hydrogen atom on my left has access to 2 electrons, so it's happy. And this guy on the right has access to 2 electrons, so it is happy. The fact that one of those electrons comes from my first atom and the other from my second doesn't matter to them. The fact that this hydrogen has 2 electrons and this hydrogen has 2 electrons, that's what makes the difference here. So that covalent bond, we're talking about sharing. Okay, so Lewis structures, the other way you might have heard of Lewis structures referred to is called dot and cross. So it's where we show the electrons by drawing dots or crosses. So if we look at methane, so if we have CH4, so we only draw the valence electrons. So carbon has 4 valence electrons. Then each of my hydrogens has 1 valence electron. So I am showing that these 2 electrons are being shared, these 2 electrons are being shared, these 2 and these 2. So I can show that exactly how I've drawn it, or I can show it with lines, where each line represents that pair of shared electrons. Let's do a molecule that is related, well, similar in some ways to methane, and that is ammonia. So nitrogen, if you look on your periodic table, has 5 electrons in its outer shell. Before I go too far into this, there is something that I would like to introduce called Octet Rule, although in about 10 minutes, metaphorically speaking, I'm going to be telling you that the Octet Rule is really a guideline. But the Octet Rule is that atoms want 8 electrons, hence octet, in the outer shell. An exception to that is going to be hydrogen, which wants 2 electrons. There are then other exceptions that get talked about in 4.3, and there are other exceptions that get talked about in 14.1. I think it's 14.1. It might be 14.2, the HL. So for our purposes today, the only exception you need to know is that hydrogen is happy with 2 electrons. Everybody else wants 8 electrons. So let's go back and look at how we draw ammonia. So how many electrons does nitrogen have in its outer shell? It has 5. So nitrogen has 5 electrons in its outer shell, and then each of my hydrogens has 1. So nitrogen now has 2, 4, 6, 8 electrons in its outer shell. Sorry. This hydrogen has 2 electrons. This hydrogen has 2 electrons, and this hydrogen has 2 electrons. All of these atoms are now happy because nitrogen has 8 electrons and each hydrogen has 2. Just like I was able to draw with lines for my methane, I can draw lines for my ammonia. So sometimes you will see that where each line represents a pair of electrons. Sometimes you will see it like this. The IB will accept. So if you are asked to draw a Lewis structure for ammonia, any one of those 3 diagrams is acceptable. The thing that students mix up, they will tend to forget the lone pair. Make sure you are drawing in that pair of electrons that only belongs to nitrogen. Okay, so Lewis structures are where we show the bonds. We talk more about Lewis in HL. Oh, I wonder why did that go? We talk more about Lewis in HL acids and bases, because Lewis acids and bases are talking about the movement of electron pairs or the sharing of electron pairs in particular ways. Okay, so all of those bonds that I showed you here are where each atom is giving 1 electron. So this is 1 times carbon's electron and 1 times hydrogen's electron. This is 1 times nitrogen's electron and 1 times hydrogen's electron. However, we can also have, so single is where it is 1 electron from each atom in the bond. Double, no surprises, is where you've got 2 electrons from each. And triple is where you have 3 electrons from each. So the stereotypical one that everybody will always do for this is carbon. So I am going to be different and talk about nitrogen. So there is a particular compound of nitrogen that I've just drawn. So if I have my nitrogen, actually, oh, sorry, I don't know why my eraser's not working. Each. Okay. For double bonding, as the name suggests, there will be 2 electrons in there that are sharing 2 electrons each. So my example for this is a weird compound called nitrosyl chloride. So for this, I've got my nitrogen, which has still 5 of its own electrons in its outer shell. But in nitrosyl chloride, what happens? I've got an oxygen over here. So how many electrons does oxygen have in its outer shell? Drum roll, please, 6. So I've got 6 electrons. So it's got 2 lone pairs and 2 electrons that it shares with the nitrogen. Let me just move that up a little bit so it's a bit clearer. So, and then it's nitrosyl chloride. So chlorine lives over here. How many electrons does chlorine have in its outer shell? Periodic table says 7. So chlorine, so 1, 2, 3, 4, 5, 6, 7. So let's check if our atoms are happy. Let's start with chlorine and work right. So chlorine has 2, 4, 6, 8 electrons. So it is happy. I don't know what is wrong with my pen today. My apologies. Then let's look at my nitrogen in the middle. Nitrogen has 2, 4, 6, 8. So nitrogen is happy, and let's look at my oxygen on the right. Oxygen has 2, 4, 6, 8. So this is nitrosyl chloride. So if I'm doing with the lines, and then remember to always put in your lone pairs, because that is the mistake that students make. So to each of those lines, remember each line represents a pair of electrons. So if I have 2 lines, I have 2 pairs of electrons. Okay. For our last one, let's talk about something that makes up close to 80% of the atmosphere, and that is molecular nitrogen. So molecular nitrogen is just 2 nitrogen atoms covalently bonded to each other. So, sorry, if I've got 1, 2, 3, and then 1, 2, 3, let's do our thing where we count up our electrons. My nitrogen on the left has 2, 4, 6, 8 electrons. So this guy is happy. Let me decrease that size slightly. Then my guy on the right has 2, 4, 6, 8. So both of those atoms are now happy. Both of them have that octet of electrons that it wants. And how we can show this is with the triple line. So remember, each line is 1 pair of electrons. So that's how we can show that. Okay, so single, double, and triple bonds. You cannot have quadruple bonds. There are too many electrons too close together, and of course electrons repel each other. So you can't have a quadruple bond, because that's always what students ask me. Okay, so in your data book, there is on 2 following tables a series of bond lengths and bond strengths. So let's talk about bond length and bond strength. Excuse me a sec while I grab a screenshot of part of the data book. Okay, so I've grabbed those snaps out of the data book. They are on the next pages from each other. So on the left, I have the bond lengths, and those are measured in picometers. We've then got, sorry, I don't know what's happening there. And then on the right, we have the bond enthalpies. So if we just use like eyeball, so bromine to bromine, the length of it is 228 picometers, which is a bit longer than bromine to carbon, which is 194. Bromine to break apart that bond, I need 193 kilojoules per mole of those bonds. That's what a bond enthalpy is. So now I've given the full definition for bond enthalpy. You don't need that full definition yet, but you will in about a topic's time. So shorter bonds are stronger. Be good if I could spell strong. S-T-R-O-N-G. Congratulations, Amy. So the shorter a bond is, the stronger it is. So do you think, just logically, so if you are holding hands with somebody or you're handcuffed to somebody, how far apart can the two of you get from each other? A fair distance, if you're talking about the distance between your two bodies. What if we handcuff both of your wrists together? You can still get reasonably far apart, but it's a bit shorter. What if we handcuff two arms and one of your legs together? Each time we add another one of those bonds, you are tied closer and closer together. And the same thing happens to our atoms. So let's look at a carbon-to-carbon single bond. That carbon-to-carbon single bond is 154 picometers. Let's look at a carbon-to-carbon double bond. That is 134. And then a carbon-to-carbon triple bond is 120. We see a similar pattern if we look at our nitrogens. So a nitrogen to nitrogen single bond is 146. A nitrogen to nitrogen double is 125. And a nitrogen to nitrogen triple is 110. So do you think that these are going to become greater in enthalpy or less in enthalpy? As I go from single to double to triple, the energy I need to break apart these bonds increases as well, from 346 to 614 to 839, and from 158 to 470 to 945. So short bonds are strong bonds. Okay, bond polarity. So let's talk about bond polarity, and this is where having the data book that has the, electronegativities is going to be useful. So we talked about electronegativity in the context of periodicity. So go back and check that if you're trying to remember what electronegativity is. Basically, it's this idea that in a covalent molecule, within a covalent bond, the electrons won't be shared evenly. Oxygen is a lot more positive. It's got a lot more positive charges in that nucleus. So it is going to pull on those electrons. The same thing goes with the other hydrogen, and this is because of that difference in electronegativities. So my oxygen is going to pull on those electrons in those shared bonds, And it's going to end up being slightly, that's what that little delta means, slightly negative, and these guys are going to be slightly positive. This is what we mean by bond polarity. There is a difference in electronegativity. What? Why did you do that? I'm sorry. Let me just find. I don't know why it did that. I'm having trouble with my pen today, everyone. I don't know what's causing it. Okay, so there is a difference in electronegativity, which means that my electrons are not shared evenly. Which means that this bond, so this bond, let me just switch colours because that is confusing. So this bond, I've done green and so let's do blue. This bond is something we call a polar bond. Now, the distribution of polar bonds in order to make a polar molecule, this is something that becomes super important in 4.3 and onwards, and really, really comes up when we start looking at organic chemistry in topic 10. So that difference in electronegativity means that my electrons are not distributed evenly, which means that I end up with a polar bond, which means I can end up with polar molecules. So I'm only going to do this briefly, but let's look at this water molecule that I drew here. Overall, you can see here, I have a negative end to this molecule and a positive end to this molecule. That's what we mean by a polar molecule, a molecule where overall one end is going to be negative and one end is going to be positive. And in order for that to happen, I need two things. So those two things I need polar bonds and I need asymmetry. So the polar bonds are what we've just discussed. Asymmetry is what you're going to discuss in 4.3. So let's look at our study guide and check that we've done everything. We've talked about what covalent bonds are. We're talking about a shared pair of electrons with positive nuclei. We've talked about single, double, and triple bonds. We've talked about bond length and bond strength. And we've talked about bond polarity being a difference in electronegativities. So if I give you a bond between two atoms, you should be able to use your data book to work out if there would be a difference in electronegativity. You can show either with partial charges, dipoles, or vectors. So vectors are where you draw an arrow on the line. Partial charges are these guys. I tend to use one or both of those. I actually tend to use that guy. And electronegativity values are in the data book. That brings us to the end of 4.2, covalent bonding. Have a fantastic rest of your day, and I shall see you next time. Bye.